now we move on to our next talk, is gonna given by Dan Goldman, and many of you might have seen his talk on sandfish, and this looks like a dry sandfish. Okay.
Thank you, Jane, and thank you to the organizers. I'm going to set a timer so that I time myself. So thank you to the organizers for having me back. I talked a little bit about some of this work the last time, but I want to give you a sort of more maybe rich picture. I should say that a lot of this work, actually this entire talk, is motivated by the work of Yves Coudert and his bouncing droplets. And so everything you see here, you can either blame him or thank him for, depending on how it's received at the end. So I'm going to tell you something what I'm going to call fundamental physics today, since this is the spirit of games and toys at this workshop. Robophysical models for general relativity and quantum mechanics, and I'll explain what I mean as we go along. I have to thank a bunch of people, including the students and postdocs and other colleagues as we move along in the two stories I'll tell you. I also have to thank some spiritual advisors. I'm nonlinear dynamics and now biological physics by trade. I don't tend to study quantum phenomena or relativistic phenomena, so I enlisted some experts along the way to make sure that I was not saying things that are too insane. And so you can judge for yourself. Okay. I also want to start, though, by why I titled this Fundamental Physics, because there was a big discussion yesterday about science and art. And in physics, one can get into a similar heated discussion if one uses the word fundamental to describe one's work. And I did my PhD at Texas, where Weinberg ruled. And so I first want to start out with what Weinberg says about fundamental physics. Weinberg argues it's better to know these fundamentals and still have a lot of interesting detail to discover. If we had the fundamental laws of nature tomorrow, we still wouldn't understand consciousness. We wouldn't even understand turbulence. That's a nice thing to say. I prefer what Anderson says, and that's going to be the sort of subtext for this talk in this very famous article, More is Different, that instead, at each level of complexity, entire new properties emerge. And the understanding of the new behaviors requires research that I think is as fundamental in its nature as any other. That is, it seems to me that one may array sciences roughly linearly in hierarchy according to the idea the elementary entities of science X obey the laws of science Y. That's going to be my definition of fundamental. But I put fun in the title because when you see what the kind of things we're doing, I can't help but have fun and smile. Okay, really what we're engaged in is understanding movement. But it's not the kind of movement that this gentleman was thinking about, and largely what that gentleman was thinking about. That's movement due to external forces, like gravity, planets orbiting stars. We're thinking about the kind of movement that this gentleman was thinking about, which is where the movement comes from drive from within. So the only movement happens because there's a drive coupled to the external environment, which provides a damping and a dissipation, and that's what enables a system like a robot or an animal to move forward. And I've come to realize these are fundamentally different ways to go from A to B. Well, it seems simple to go from A to B. Movement emerges from myriad interacting elements and systems, and so from the reductionist fundamental point of view, the only interesting thing really to do is then to study all the little parts. And once you got all the parts, you're sort of done. You've gotten the fundamentals. But of course, you can ask the question, can we predict such a simple movement from such a reduction? And an excellent example is provided in the best robots of the day, which tend to violate this idea in very dramatic and expensive ways. And I've shown this video before, and it's fun to poke fun at millions of dollars spent by DARPA 2 years ago in the robotics challenge, and things have improved, but not to the level that one would allow one of these things in your house to take care of your child. Okay. Before I go on with my talk, because there's a component of fun in this that I want to emphasize, and it started actually with this gentleman who was here, who I got to meet as a high school student. And a long story, but the folks who introduced me, said, Tim, give this young man some advice. This was before I was going off to college. And his advice was, which I thought was ridiculous at the time, is find a good mentor. And turns out that's the only advice that really has mattered for me. I've been lucky to find, I count 3 terrific mentors, PhD supervisor and postdoc supervisor, But the mentor who motivates a lot of what I'm going to say is a guy named John King, who I worked in his lab as an undergraduate at MIT. And the reason I bring him up is because King was a fascinating guy. I don't know if any of you have known him or met him. He basically started an entire program of experimental, tabletop, hands-on introductory physics course at MIT, which lives to this day. He won the Oersted Prize in the year 2000, and he had this idea that really, this is his bit of discussion about why using computers to understand the natural world is not sufficient. In fact, he says, in case the availability and acceptance of such unprecedented amounts of material with little depth, despite efforts toward interactivity, does not do much to develop the subtle basic skills of observing with all five senses. Experimenting, describing, measuring, modeling. The hands must be involved. There's no substitute for fooling around, for hands-on fooling with the real stuff. And that's sort of the basis for the fun of this talk. Okay, it turns out that hands-on robotics, despite the millions of dollars that are being spent by federal agencies in our country and here, hands-on robotics is now quite possible. In the past, robots have been hard to make flexible, hard to add sensors, hard to sort of use and test in a physicist's laboratory. If I want to understand animal motion, well, it's often hard, as Mimi beautifully pointed out yesterday. It's hard to make animals do what you want them to do on command. We also have limited capabilities to try to understand organism movement. But in recent years, there's been an explosion, largely driven by the hobbyist industry, of low-cost but smart and powerful motors that one can program quite easily, controllers that one can program quite easily, sensors, and in addition to 3D printers, which allow you to make cool robots which actually do interesting things in the real world. This was made by a biology postdoc in my group who had never made a robot before he came to my group to be a postdoc. Okay, we call these robophysical models. And they've infested my lab now in the sense that everybody, not everybody, but many of the students that come to Georgia Tech love robots and want to make robots, and so I bring them into my lab and they make all sorts of devices, some of which I'll tell you about today. We call this robophysics because traditional robotics is really sort of descended largely from control theory, and the idea that many of my colleagues have is that if you build a mechanism and then develop a smart, interesting controller, you can make a robot to move from A to B in the world. And this is actually proven to be fantastic in sterile environments like factories, but not so great in more realistic, more complicated environments. And one thing I think that's interesting is what one does as one's a physicist approaching the subject is look at these things as dynamical systems and then explore the range of dynamics, be it successful, interesting locomotion, like my colleague Howie Choset's robot going in pipes here, or failed, what my engineering colleagues would think of as uninteresting motion, failed motion of this robot, same robot trying to ascend the sandy slope. We call this robophysics. We had a review article last year. And if you want to hear more about it, this will be my last pitch. For the third year running, we'll be running our robophysics focus session at the APS March meeting. Pekka Hosoi will give the invited talk, and by popular demand, we were asked to run a hands-on robophysics tutorial to show students and faculty how one can make these little robots and explore the kind of interesting questions that, for example, you asked about making the shell of the beaver ball into... Easy, trivial. Okay, let me get to the meat of the story here. Two stories, one about robots that scatter off obstacles in a way that mimics subatomic particles, and the other is self-propelled cars driving on membranes mimicking Schwarzschild precession. And I don't know if these are fundamental, but they've certainly become fun for us, so I wanted to tell you about them. Turns out that small robots moving in homogeneous environments, there's a lot of work that has been done to actually improve the performance of little robots in sort of relatively pristine environments, like a flat ground or even a sandy slope. We've made some progress in recent years. I had to include this because as I was eating dinner last night, the waiter told me that just down the street, Amazon, down the street from here, Amazon is testing its drone delivery service. Did everybody know this? Okay, yeah, it turns out that this Cambridge, UK is the place where the drones will begin. And you can do that. And so flight and walking and moving on sand and swimming. This is a cool little robot that recently inspected Fukushima. But there's our future right there. No more human knocking on our door. Thank you, Cambridge. But locomotion in environments which are heterogeneous, particularly terrestrial environments, is much less studied and much less explored. And here's two of my favorite examples. This is this same robot, cockroach-like robot that was running so well on hard ground, failing when it ascends a gravelly slope in the Mojave Desert. And this is my colleague Chosit's snake robot trying to go through clutter. Oh no! In the way that come back. In the way that a real snake would have no trouble doing. And these are, of course, useful for the engineers. So both of these stories I'm going to tell you started with very, very naive ideas because I don't know anything about quantum mechanics, nor do I know anything about relativity. I said to myself, well, a robot running over hard ground I can sort of understand, and on sand we've begun to understand, but what about heterogeneous environments? Well, I'm a physicist, so the first thing I think of in a heterogeneous environment is I go to something like Lorentz, the motion of electrons in metallic bodies, or the other Lorentz, scattering off moguls, or Svetanovich scattering off billiards, and I say this is a scattering problem. All I have to do to understand statistically the long-term behavior of a robot is understand how it collides with a single obstacle, and then I can just make an infinite lattice or a random perturbation. That was my idea. It's not a great idea, but it was an idea. So we started doing this. We started made a robot that basically makes a robot, kind of picks up a robot and picks up a boulder and puts it in place over and over and over to do a lot of robophysical experiments to get lots of statistics on the scattering. The experiments look like this. They're done completely automated. Fei-Fei Chen was my student doing it. The robot hits the boulder and scatters to some extent. And I'll tell you the naive thought when we started this, and what most of my engineering colleagues think of if they do pay attention to colliding with obstacles, which is rare, is that, okay, you collide with an obstacle and you go scattering off some direction. But here you'll notice something funny, that if you just blur your eyes, this looks like a particle coming in and being attracted to the boulder. Okay? And you can see why, of course, the balance of torques, but you can do this lots and lots of times and you can get some statistics. And this is what it looks like. And it turns out that this sort of pattern of attraction sometimes, but repulsion other times, is insensitive to our physicist types of boulder shapes and sizes. And largely depends on what surface, the leading or trailing part of the boulder you hit. So that was sort of interesting. We then put other things in the way, and this was a suggestion of an engineering colleague said, well, our little legged robots have trouble getting over railroad ties and logs. So what happens there? We put this thing in the middle, and lo and behold, it scatters left and scatters right, but never goes straight. That's kind of funny too. Okay. By the way, this is actually useful. Knowing something about the scattering pattern, we've been able to now, working with engineering colleagues, do a sort of anticipatory control. If we know where we're going to hit roughly on the boulder, we can take an action before the robot gets there to anticipate the dynamics, and then to correct that before the robot goes careening out of control. Okay. I had a realization as I was teaching Classical Mechanics 1 to undergraduates this semester, which I should have had when I started this, that this is not scattering in the slightest. And of course, I had to go to Landau and Lifshitz, collisions between particles, and I told my class this basically. In many cases, the laws of conservation of momentum and energy alone can be used to obtain important results concerning the properties of various mechanical processes. If you noted these properties independent of the particular type of interaction of particles involved, and in Classical Mechanics 1, we go through 1D and then 2D and all sorts of examples. In our active collisions, or our collisions of self-propelled particles with the environment, we have neither energy nor momentum conservation, at least that we can detect. Of course, there's real momentum conservation, but it's lost to us because we don't pay attention to the Earth or the environment, largely. And of course, we don't have energy conservation. So these are not the kind of collisions and scattering problems that I grew up studying. And in the absence of knowing what people have done in these kind of, haven't seen a body of literature, we're just going to call them for this talk active collisions. Somebody can correct me later. So then the question is, they're common if you sort of go from that perspective, particularly in snake-like robots. So we decided to say, how can we use, avoid, or manage such collisions? We worked with some engineers to try to understand, to build a control sort of scheme to make this robot do better, and we succeed a little bit, but it was complicated and we didn't understand it. So we said, let's just do the physics, the robophysics version of it, and we'll go very, very simple. We'll start with a robot. The robot has wheels, and the robot's made of servo motors and 3D printed, all very low cost but precise. The motors in the robot's back drive themselves sinusoidally, which are coupled to each other in a chain, so you end up getting a wave that goes down the body. In free space, that would just result in a robot waving, but when you couple it to the ground with wheels, it moves in a kind of snake-like movement pattern. And what we said is our model heterogeneity is we'll just stick a bunch of obstacles in the way, we'll put a post there with some spacing. And that's the experiment. The key ingredient here is the robot doesn't sense, it's sensory deprived. The only thing it can do is control its pattern of self-deformation in its frame. And that doesn't get violated, by the way. The motors are really strong and good. So basically just does that. And any reorientations you see are a result only of torques and forces of the wheels on the ground and the posts against the body. That's the game. And so then, from my naive picture, in the active scattering picture, will we expect the robot to scatter more like a wave or more like a particle, or will it have aspects of both? And actually, that was an excellent introduction because that is the same thing we're thinking about in your talk. So here's how we did it. We didn't have an automated system at the time. We do now. So our automated system was this poor graduate student, Perrin, who was fantastic and patient, basically taking robot, putting it in various initial conditions. There's a certain box of initial conditions, which then repeats. I could amplify on that later, and doing it over and over and over. And with nice, low-cost, high-speed cameras, which automatically track positions of markers on the body, we can record all the kinematics we like, thousands and thousands and thousands, literally thousands of times. And then you'll see sometimes the robot scatters left, and sometimes it scatters right. And you can then track these things. And this is the initial condition box, and the different tracks. There's two different representative tracks shown here. And so here's what happens. What I'm going to do now is provocatively show a movie where I basically show each trajectory of a head on a different experiment and just sum those up, build up that pattern over time. And this is what we see. One is the head, and the other is the sort of average body of the robot. And what you see is that the robot basically comes out at preferred orientations. It comes either straight, or to the right, or to the left. You can do a histogram of that in the far field, and you basically get a pattern like that. So we were kind of happy about that, and it sort of fit with what Yves and John Bush had been looking at with droplets, and that got us to keep going. Because what can we do in our system? Well, very easy. We can change the spacing between the posts. We can squeeze them down or make them wider, and you find something sort of interesting. Here's the distributions as a function of increasing spacing between the posts. And you'll note that as the spacing, I like going this way, as the spacing decreases, the distribution gets wider and wider and wider. And we can measure some characteristic of that distribution, call it theta q, a 15th or 85th quantile of that, and that basically measures the spread of the distribution. And you find that as you try to localize the robot in space, make it go through a post, between two posts, it responds by spreading further out in space. So it's sort of like an uncertainty principle for robots. And this is experimental data, and we can see this in simulation as well. I should say that there is a formula that one can plop down on this, and it doesn't do a terrible job, the far field Fraunhofer diffraction formula for describing this. There's no interference, of course, with the robots. It's only one robot at a time, but somehow this formula seems to work. As I said, we could do simulation. These are not trivial, these multi-body simulations, so we enlisted a big simulator, and Dan DeGroot at Wisconsin and his student. To get it right, we actually had to measure the frictional anisotropy of rolling wheels, which is a ridiculous thing to measure, Lego rolling wheels, but we did it. And we did it by strapping these Lego wheels to a $40,000 robot arm and rolling them in various orientations relative to their attack angle. And you can get that function, and if you plug it in the simulation, you can get a pretty good match to the experimental data. Here, for example, is experiment, and here's simulation, different scattering patterns as a function of spacing. And then with the simulation, you can do more things, as Mimi said yesterday as well. You can try to explain what sets that fitting parameter in our uncertainty principle relation. Remember, the fitting parameter basically is arc sine of big D over D, where D is the spacing between the posts. It turns out what sets that parameter is if you plot that number that you get, the fitting number that you get against this quantity is just the amplitude, the projected amplitude of oscillation of the head. And so that's the thing which is setting how much it's going to scatter for a given spacing between the posts. Kind of interesting. And then I love this quote. I've always loved this quote, where Feynman, in the double slit experiment, talks about, well, it's absolutely impossible to explain in any classical way, which has the heart of quantum mechanics, why you get a sort of interesting looking distribution when photons or electrons go through double slits. Well, it turns out that it's not impossible if you consider non-classical type collisions. These active collisions open up an entire range of interesting dynamics, which you can see. So this is actually the double slit experiment from our robot. How about that? That kind of surprised us. Okay, while we're talking about great minds, I figured I had to show you this. This is sort of new. What happens if we try to observe the robot? Well, observation to you and me is with photons, but the way I want to do it if I'm playing the observe in our quantum mechanical game is I let the obstacles, the colliding obstacles, move a little bit. And so you can do this in simulation. We're working on this experiment too. We do it by making this basically a frictionless surface with a bunch of these posts, and you let the posts slide frictionlessly, and that post array has some mass associated with it. So the heavier the mass, the less it's going to be deflected by the snake, and so here's an example. Watch this. You can barely see any reflection of the array. On this one, it's going to go through, bonk, and you see a little bit of deflection, right? And then watch this one. This is a sort of very light case. Whoa. And there you see it really move around.
Can't be frictionless. It can't be frictionless, the table. Otherwise, that little impulse, it would move forever.
It would, but except that you'll notice that the snake brings it back.
Oh.
We have a version where it does move forever where we let the pegs go through each other, but that's not this one. We see qualitatively the same thing. Here's what you get. Here's the probability to find the robot at different angles. And here's the probability to find the array's velocity at certain speeds after post-collision. And you see that it's a delta function here, the array doesn't move, and pretty broad over here. Where if this guy is broad, the angular distribution is broad, and this guy is more narrow, you can plot these things, and one goes down and the other goes up. And so the more you observe the robot, it essentially erases the diffraction pattern. I thought that was kind of fun. How robust is this? Well, in my lab, we spend a lot of time studying animals, and it turns out that we have found that one of our little animals that we love for other reasons basically is a robot. It likes to play this wave down its body. It lives in the deserts in the southwest U.S. Likes to play this wave down its body, and it rarely deviates from that. And so this industrious crew decided to chase lots of snakes over and over and over, and they did that. Time. Oh, good.
Oh, you have plenty.
Play. Good, good, good. I just want to make sure what I'm going to...
10 minutes.
Oh, actually, mine says 17 minutes.
Oh, is that right?
Because I have 40 minutes, right? Good.
Well, I don't know.
Yes,
It
I
says 10:40.
Yeah, but we started late, so I'm timing. I'm gonna get through all this. So there you do it thousands and thousands of times, and you cull it down so you only get the runs that the snake goes straight starting and then doesn't do weirdo behaviors.
This is a real snake.
This is a real snake. This is called the Mojave shovel-nosed snake, but it acts like a robot. It's hard to break it out of its thing. And by the way, here's what you get, and then if you average in the near field and the far field, in the far field, it basically shows 5 peaks. And Perrin, the student, has this beautiful model which basically has the simplest amount of control in it of how the body responds to being perturbed, which reproduces this with no fitting parameters. So we think it's pretty robust. So let's make the fracs too. Okay. Well, speaking of far field, because I knew Michael Berry was going to be here, I had to put in something for near field. Because my spiritual advisor, Mike Chapman, who studied with Dave Pritchard, said to me, boy, you see far field type diffraction effects. What about near field? And so I said, what's near field? Because we didn't learn that in my undergraduate. Well, a famous near field diffraction effect is called the Talbot carpet, and I'm not going to say too much, else I'll get hollered at. You can read this beautiful piece by Berry et al. In Physics World. But this is Fresnel diffraction, and it was originally studied in light, and it's called the Talbot carpet. And the sense is you start with a monochromatic wave of light, and you make it encounter a grating. And if you sort of look at if you make an image plane at distances away from the grating, you find that at certain spots away, the grating image appears very sharply. And at other spots away, it appears sharply, but laterally shifted by I guess, pi. And then there's lots and lots of other phenomena. You can read all about it in his various papers. So we said, well, can we see this? Oh, by the way, Mike Chapman got excited about this when he was a student and saw this in single atoms too. So you don't need light to do this. You can actually, matter waves will show a Talbot effect too. So we said, how are we going to see this? Well, we don't want to send a lot of robots in because that's a pain in the neck. So Jennifer had an idea and said, well, this is the scattering pattern from one robot. Let's just tile the plane with these things, which is sort of fair because in the ensemble limit, right, if I did the experiment millions and millions and millions of times, this is what I'd get. This would be the probability to find it. By the way, in terms of art, this is my best attempt at art, so I'm not an artist. Anyway, that's what we do. You can stop it, and that's what it looks like. You can zoom in a little bit, and lo and behold, here's the posts. Here's a bright spot, basically. Here's a bright spot at one wavelength away from our robot, Z over E naught T, and here is the laterally shifted image at half. And we're just exploring. This is all very new. I just figured I had to put it in. Okay, while we're at it, let me tell you one last thing, because we have some understanding, and this is largely due to Jennifer, the postdoc, of where the hell this stuff is coming from. And it's actually a beautifully simple story, and it is completely because of these active collisions. And the reason I'm so excited about that is because we've been through several theorists trying to analyze this problem, and all of them have started out with the Landau-Lifshitz scattering approach, and all failed miserably. And I love that when theorists fail. So here's what it is. It basically takes advantage of this phenomena that when the head comes into the post, it stays grinding there until it reaches a tangency condition and then can pop off. And so it echoes what you were saying earlier about now you have a waviness interacting with contact. And there's an interesting story in the sense that the longer you spend grinding your head against the thing, the further you'll scatter for a single post. And there are certain spots on the post where you scatter more strongly. You spend more time grinding. You can imagine if you hit sort of here, you spend a lot of time to wiggle back and forth before your head reaches tangency. So that explains the single post. And then the beautiful bit is how does the interference happen? Well, it turns out that trajectories, I have a bunch of posts, trajectories that would have basically missed the 0th post that we're analyzing, when you add other posts, suddenly there's other posts in the way. And those posts are stationed at the sweet spots for scattering. And so you see that there's now a mechanism by which grazing collisions can be turned into large amplitude scattering collisions. And we have a whole model worked out. And we're today about to submit this paper finally, but nothing's submitted yet. This also suggests control strategies. Well, here's something sort of funny that the last bit I'll say on this little guy. So here is, again, the single post. And here we have the distribution. The probability to find the robot is a function of angle. In this case, angle 0 will be right behind the post, and x and other angles left and right will be positive, negative. And the full distribution, a lot of the time the robot just completely misses the post. It just sinuously winds its way around the post. But and that's about half of the time actually, but about half the time it actually hits. And when it hits, you get a distribution that looks like this. And I'll provocatively say that the greatest probability to find the robot lies in the shadow of the post. And I'll say that because most of you know what's coming. This is the famous Fresnel-Poisson-Arago spot. You can barely see it. None of these pictures are magnified. And this was it's a wonderful story, and I've learned a little bit of the literature. Starting with Newton, part of the way light is corpuscles. Young says, I see interference. Fresnel says, I've got a theory. Poisson says, that's crap. That says that if you have light in it, you put an obstacle in front of it, you should see the greatest intensity behind the obstacle. And Arago goes and does the experiment, and lo and behold, there's the spot, and now anybody can do it. You can do it also with molecules. I love this paper. Matter waves, too. And so that's sort of what we're seeing. Okay, whatever that means. I think it's just sort of fun to think about, and this is why I wanted to give this talk, to think about connections to other wavicle-type scattering systems. So here is one of my favorite experiments, done many, many years ago, but this one I love. This is Bach's work from 2013, and this is the diffraction pattern built up electron by electron by electron. Here, of course, is Cuderi's beautiful pilot wave work. This is actually a paper which I didn't know anything about until my other spiritual advisor, Zangwill, who's now a historian of physics, told me, oh, you know that Taylor, before he did fluids, worked on this kind of stuff. I guess everybody in this room knows that. This is great, right? He was, I guess, a graduate student. Does everybody know? But the best part of this is it took 3 months. Feeble light diffraction. He basically set the experiment up with a candle and a darkened little glass plate, and then put a grating there. And I think went away for 3 months and came back, and there was a diffraction pattern. The paper says that. There's no figures in the paper. There's barely any data in the paper, but nevertheless, I believe him. And this is what everybody cites as the first evidence that light, single photons could display this kind of particle wave duality. Okay, that's enough about snake robots. I have about 5-10 minutes, I think.
That's so. Okay, let's
Okay.
see. Yeah, 5
No, it says 10 minutes on my thing.
5 minutes.
10
That's
minutes.
5 questions.
Okay, 5, and I'll take my question time. Okay, here's the next one. So here's my advisor on this one. He's the chair of our department now. He's a numerical relativist. His name is Pablo Laguna. And I have gotten tired of all my colleagues at Georgia Tech boasting about LIGO and gravitational waves, and there's too much damn press for this stuff. It's beautiful, it's fantastic, what an achievement, but I wanted in on the game. And so I said, how could we do this in the laboratory? And of course we can't, but just humor me for a minute. I was always inspired by Wheeler's famous quote that space-time tells matter how to move and matter tells space-time how to curve. And so I said, well, geez, we should just do the old bowling ball trampoline experiment. Everybody's seen these, right? And by the way, you want to look for vituperation. You want to look for nastiness in the literature. Go look up online what's wrong with doing this. Because it turns out that this is not a good model for general relativity. Everybody knows this. Well, it's not. I've learned it's not a good model for general relativity for many reasons, because real gravity is actually important in this. It's not the curvature of the space which is necessarily driving the dynamics, and these are space-like curves for the embedding diagrams, and that's not important. But anyway, they're not good models. But I decided to press ahead anyway with encouragement just to see what we could do. I said, at least we can minimize extrinsic influences like gravity. So we did this. We took spandex, and by the way, here's a spandex fiber, which I think is sort of artistic. Like large spandex sheet. We make little robot cars which have solar panels so they never run out of energy, and we make a central depression. We put little IR reflective markers, and we basically can make the car drive on the membrane, has good sticky wheels, and with an actuator which can set the central depression in the membrane, and we can film all this stuff with a motion capture system so we can get good data and watch what goes on. First bit, we want a car that drives straight in the absence of curvature. That's part of the recipe. So these two folks, she's a fantastic postdoc. She made this car with a nice differential in it and a little caster and a solar panel and a little motor controller, which basically goes straight on hard ground. We have our spandex. I have a theorist on the project, and this is as much of the experiment as we let him do. We let him tap. Why does he tap? Because I wanted to show you that there's cool waves that come through the system. So the system can support waves of curvature change in the membrane, deformation in the membrane. And also, it's a nice technique. You bond little IR markers to this spandex sheet, and then basically you can reconstruct the deformation field almost for free. On the membrane, the car drives straight in the absence of curvature, and it also responds nicely to the curvature of the surface. So here's Yasmin using the force to sort of let this thing chase her around. I think that's kind of fun. And of course, you can put it around central depression, watch it go round and round, and even measure the curvature field. And so we're interested in the trajectories that are going to occur because of phenomena like this. Here's one of the dynamics we observe. We see sometimes asymptotically stable closed orbits. Look at that. And there's a projection with time in the y-axis. So, just by the way, just for what's going forward, the radius, we'll call the radius of this car, the distance from the center to its current position, and you can measure the radius as a function of time, and it's doing this sort of transient behavior and then gets sort of small. That's sort of our circle. But we also see kind of trajectories like this. Let's see if that'll play again. And there, you see a trajectory that never closes into a circle. It goes between an R min and an R max. And this is what's called a precessing orbit. And you can measure, for example, the delta psi, the angle of precession between successive R maxima. Keep that in mind as we move forward. But we sort of played around and have found all these kind of amusing orbits in our system. This, by the way, Guidry, I don't know him, but he has a kind of terrific lecture notes online if one wants to learn about general relativity from the ground up. And he has, and I'll explain this in a minute, he has classified the different kinds of orbits one can get in a Schwarzschild solution to general relativity. And you can get circular orbits, bound precessing orbits, scattering orbits, and plunging orbits and we get all these things. Sometimes the car goes straight into the depression, sometimes it scatters off, sometimes it gets, anyway. Okay, but look at this. This is what got us excited in this problem, and my colleague excited. Why did these precessing orbits excite us? Well, because Newtonian gravity doesn't have them, which I tell my classical mechanics class too. They close in Newtonian gravity. This is a great animation from Wikipedia. Whereas in the Einstein-Schwarzschild solution for a spherically symmetric object, you basically have an effective potential which looks like Newtonian gravity, our standard centrifugal potential, and this correction, which is a little stronger. It's an r to the cube, so the force is a little bigger if you're closer. And it turns out that one can derive that the amount of precession in the Schwarzschild solution causes elliptical orbits to precess by this amount, which is 6 pi times g, big M plus the little m of the particle orbiting, wave speed squared, semi-major axis, 1 minus eccentricity squared. Okay? Fine. We can measure all this stuff in our data. We can measure A, we can measure E, and let's just see what we get. Well, here's how we control our central mass. We have our actuator, which can drag this down to different depths, different depressions, make more curvature or less curvature. We also systematically vary the initial position of the car relative to the center, the R, and its orientation. And here's what you get, or a lot of experiments, and this is averaged. I don't like how they smooth this data, but this is hot off the presses, and so I'll yell at the students later. But basically, they sampled a lot of points. We like to get good systematic data. But here is for a low depression and a deep depression. Deep meaning a heavy mass. And what you see, heavy mass, big curvature, that in the bluer it is, the less it precesses, and the yellower, the more it precesses. And you see that for shallow depressions, you get a large region of parameter space where you get these beautiful precessing orbits. And for deeper, you get a smaller region of precessing orbits, but more closed orbits. They're more common with a greater central depression. Okay. So then we decided to do the next bit. We said, well, let's just pretend they're Schwarzschild-like, and then just plot things. So here we're plotting 1 over, remember that the precession angle for a Schwarzschild solution goes like this, 1 over A, 1 minus E squared. So we plotted 1 over A, 1 minus E squared versus the precession angle, and lo and behold, we get curves. These are for different depressions, which are not terribly approximated by straight lines within the scatter. And as I increase the depth of the depression, the slope of this curve increases. And hot off the presses, my student plotted this last night, and basically this quantity, this Schwarzschild-like quantity, scales very nicely with the depth of the depression. So it's sort of interesting. Except there's a total cheat in this plot. And since I have it, and this is what we realized, does anyone see that? Of course you see that, you're mathematicians. That's an absolute value. And it turns out in our system, we've discovered, the orbits precess backwards. So in general relativity, it precesses in the way that you're orbiting, if you can see that. In our system, it's a little harder to watch a precessing orbit go in the opposite direction, but that's what it does. But if you plot the absolute value, it's okay. So we don't understand any of this stuff. Okay, fine. Ongoing. What we really started with, I told you, was the Wheeler sort of idea that space tells matter how to curve, matter tells space. And I know this is not the right model for general relativity. I understand we're not, this is space-like, but I think that there's something captured, and this is what I wanted to give this talk on because I need some help. And it's sort of fun because now the cars can influence each other at a distance via changes in the membrane. And we think it's fun to play around with this sort of stuff. This theory student has also actually got a very interesting dynamical model, which captures a lot of what we see, basically curve fitting to extract something about the sort of virtual potential in our system. And I'd be happy to tell you more about that. Okay, so I think I'm going to close here. In summary, this idea of robophysics and hands-on robotics is new, we think, and available and accessible to students and faculty and researchers, and produces wonderfully interesting surprises, at least to me. We've studied something which is not quantum mechanics, but we see interesting effects like active collisional diffraction, uncertainty principles, measurement effects, Talbot near-field effects, the Arago spot. We have something which is clearly not general relativity, but we put a single car into formal memory and we see Schwarzschild-ish solutions, precessing, plunging, and scattering orbits, although they precess the wrong way. It's fun. I don't know if it's fundamental, going by the Weinberg-Anderson discussion. I'll leave that for you. But there's something very cool about these robots, and I just want to close because I know there's going to be some collective work that we've been spending a lot of time on recently. We get the idea that we want to make little robots that could actually grab onto each other and pull onto each other. So we made little robots with little arms, and we can send sound to them. They're lightweight, low power, they last on batteries for a long time. We call them smarticles, smart active particles. And then we had the idea, well, all metazoa are living systems made of other living systems, but I don't know any robots that are made of other robots. So how could we do that? And we've now done that. And you do this because you can make these so quickly, cheaply, and beautifully. Here's a set of smarticles confined in a ring. Each smarticle on its own cannot move. But when you put them in a confining ring, they diffuse around by kicking each other. And then if you turn a light on, the light makes one freeze. And it turns out that sets a bias in the system, and the little robot will follow the light and phototax towards or away from the light. Anyway, that's all I have to say. And my time is up, so thank you. And I'll take a question.
I have two questions. First of all, I noticed for your GR-like
Yes?
situation, these robots depress the membrane a little bit. So my
They
first
do.
question is there any physics there? And my second question is, what about just having a ball in wouldn't you have some of these orbits by simply throwing a ball in a G?
You do and you don't. Actually, there's interesting discussion in the literature, mainly in the American Journal of Physics. You get Kepler-like orbits with the wrong power. It turns out it's instead of 3/2, it's 2/3. But they always go spiraling downhill. You only get plunging orbits. So we wanted to take that part out. The real game in this actually is to add a kind of adhesive tape where the robot onto the wheels, where the robot actually is only responding to the intrinsic curvature of the membrane. And that's where we've been. If we keep going with this, that's where we're headed.
And what about the depression?
The depression that's an effect of gravity, of real gravity, right?
Yes.
So, I can't decouple that. I don't know what I can decouple and can't decouple yet, but clearly a robot knows about another robot because it creates a local curvature, and so that part is kind of right, but it's, maybe it's a little crazy.
Yes. One of the features you emphasize in these really gorgeous demonstrations is that they illustrate abstract ideas from elsewhere in physics.
Correct.
Now, with the snake, let me share something with you.
Yes.
Many years ago, when I learned why de Gennes got his Nobel Prize, one of the reasons was that he'd identified a motion of polymers which he called reptation. Right. Now, I realized, and this is what I want to share, that you can use the motion of a snake as an illustration of a non-holonomic constraint in a one-dimensional field theory. A snake is a curve, it's a one-dimensional field. It's constrained in that at any instant dt can move only parallel to itself. But that doesn't determine its motion because it has the freedom to change the curvature at its head.
Yes.
And you illustrate that beautifully because your robots, so the way in which they don't simply move in a predetermined way, is that either independently or when they hit the obstacle, their heads move. So you're illustrating that. So it's a non-holonomic constraint in a one-dimensional field theory. That's just a comment.
Well, thank you. And actually, I have a comment for you that the other part of the talk, which not this talk, but another, it turns out that the geometric phase, which you worked on years ago, and which Wilczek introduced from the physics literature for locomotion, turns out to now have been made useful by some of these engineers I talked about, and we can use it to describe how movement occurs via self-deformation. We can get the gauge potential for a whole lot of classes of systems. Yeah, and I'd be interested to talk to you.
There's a
I
question in the
have two
back.
comments. One is about the general relativity.
Yeah.
The model is not such a bad idea from the point of view of general relativity because all dynamics problems can be converted to geodesic problems in a space-like surface using the method of Jacobi, which is familiar from aerodynamics. The metric depends on the energy. It's not independent of the energy. So you can work that out in the case of the Schwarzschild solution. I have no idea whether it would agree with your simulation. So you shouldn't be apologetic about that aspect. The second point relates to your quantum mechanical model.
Yeah.
When I looked at that, I remembered that there's an equivalent formulation of quantum mechanics involving a Madelung fluid approach, which I think you may have been alluding to. But basically, you just make an artificial fluid, an analog fluid from the Schrödinger equation, and you're squeezing that fluid through a barrier, And that made me think of wiggly world lines, which free flow world lines, which are awfully like your snakes. Now, it's just a picture. I mean, this is a toy.
And Eve,
Maybe it actually works.
Eve, John Bush, I know, has looked at Madelung, but Eve could probably speak more, certainly speak more intelligently to that comment than I.
Yeah, those equations are better known when they were rediscovered by de Broglie and Bohm, but they used philosophical words to describe it. It's the same.
Yeah, the
It's
paper
really
is a
muddled,
month
yeah.
after
Exactly.
Schrödinger's paper.
Astonishing, yeah.
Everybody should know that paper, particularly fluid dynamicists.
So I really enjoyed the videos of watching the robots fall over.
Okay.
But it put me in mind of a Gandhi quote. I don't know if you know this, which is first they laugh at you,
Yes.
then they fight you, and then you win. I wonder if any of this tells us something about the future of human history.
Yeah. Who's you in this case?
Us versus the robot.
Yeah, we have no chance. I mean, you know, we have no chance.
We laugh.
Yeah. Right. Yeah. I mean, we shouldn't be. But, yeah. What else you gonna do, I guess?
Well, I have many questions, but okay, I will limit myself to two. The one is in when you do diffraction, you want to have a monochromatic light,
Yes.
and so how monochromatic are your snakes? Does it depend on their length, for instance, or is it to what accuracy is the wavelength defined?
Yeah, I mean, it's weird, right? Because we have a wave packet in some sense, right? We have an infinite number of waves. So that's sort of point one. Point two is we have started to play with, in the simulation, adding different numbers of waves on the body. And it doesn't seem to change things qualitatively. But I don't know how to think about, I mean, we can control the amplitude of oscillation of the wave quite well, and thus which sets ultimately the wavelength. Beyond that, I don't know what exactly do you mean by monochromatic. I mean, they're not infinite wave trains, right? It's not.
What wavelength?
Oh, we have coffee. Oh,
So
no worries.
is afterwards. The other question was linked with, in our experiments, the fact that it has some similarity with quantum mechanics depends on what we call the memory, which is a sort of that the system at one instant is sensitive to waves
Right.
that have been emitted in the past and which still drive it.
Correct.
So is it what you see when you have a collision with a snake, that the back of the body undulates in a way that is disturbed and that has memory of its previous motion or something like that?
So I'll answer that in two ways. One, when we started in on this, I wanted, following your work, I wanted to make the kind of robophysical analog. So the idea I had is, okay, make a long robot that actually is a bit compliant in its ability to so the head would hit, and those waves would get kind of scrunched up, and that would propagate down the body, and that would be the sort of memory.
It wouldn't be a proper constraint, yeah.
So it turned out that my student convinced me to start with the simpler case, and she was right. But that was where I thought the memory would come in. I think that right now there's a kind of non-locality in this problem, in the sense that it's not just a simple self-propelled particle. This is, I guess, the bigger idea here. It's a self-propelled particle which has spatial constraints or extent. So maybe that's what plays but we've done things like make the robot more or less compliant. In other words, right now it has no ability to change the angles as a function of time. The motor controllers are very good. But you can relax that. You can set limits. And then, actually, you see for a good set of parameters that this phenomenon remains largely set by rotations, sort of overall torques of the body from the post and from the wheels on this distribution of forces on the wheels on the ground. So I don't know what the equivalent memory parameter is to your system, but I think it would be worth thinking about. I should say also, to answer your comment, the other analog that my colleague Zhang Wu told me, actually, which is something which many people here probably know, but I didn't know of, is Duane's. Does people know about Duane's picture of quantum mechanics very early on? he and Compton, and actually Ehrenfest wrote a paper on this. Dwayne had this idea that you can get Bragg scattering by basically an electron, or a photon, or whatever, is only allowed to deposit quanta of momenta laterally to and you get the whole system. And we've seen, there's these other sort of early pictures of quantum mechanics, which are sort of fun to think about.
You might consider an extension to your work with that axisymmetrically deformed surface.
Yes.
Gently by putting a beaver ball on it.
So, we've done that. In fact, we don't call them beaver balls. We call them spheros. Does everyone know the Sphero toy? If you don't know the Sphero toy, if you've seen Star Wars, the little robot BB-8, these came out around Christmas a couple of years back when Star Wars launched. It's a little spherical robot that has a little motor driver in there. It actually had 2 wheels, so it can move back and forth, and it rolls around. Look up Sphero. So that was the first thing we did. We put a Sphero on the thing, and it goes. And then I wanted the sort of constraint that the robot, because with the Sphero it can rotate, and I didn't know how to, maybe it's the better analog, but we could certainly mess around with all these things.
Okay, with that, thanks, Ben, for such a fascinating talk.
Thank you all.